Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 22, the Matrix class. Well, we've done a lot of mathematics. We've learned about vectors and matrices with the goal of creating geometric transformations in a single data structure, which we learned was called a matrix. We spent a lot of time deriving all the different kinds of transformations we want, and now it's finally time to get back into coding. So just as a quick recap, what have we got? We learned about a matrix for scaling, right? That matrix scales elements, the x, y, and z coordinates by r, s, and t. We learned about rotation matrices. In 3 dimensions, you can rotate around the x-axis or the y-axis or the z-axis. And for each one of these, we have a different matrix. This first matrix rotates around the x-axis, this one rotates around the y-axis, and this one rotates around the z-axis. Then we learned about translation, and it turns out we can't represent translation in 3-dimensional space with a 3x3 matrix. So we learned about homogeneous coordinates representing points in 3-dimensional space as a 4-dimensional vector where that last coordinate is 1, which was something we had seen in OpenGL before, and now we know why that is the case. To translate a point, xyz, by the vector mnp, you would multiply it by this matrix, a translation matrix. And then finally, to create that perspective effect, we learned how to derive the perspective projection matrix. This one took a while. It's defined in terms of the shape of a frustum, right? And that's defined with 4 different parameters, with the near plane, n, or the near distance, the far plane distance, f, the angle of view, the vertical angle of view, a, and the aspect ratio of the scene, we'll call that r. And so anytime we want objects further away from the camera to appear smaller, we're going to need to use multiplication by this matrix. And so those are the 4 different matrices which we're going to need to create, along with some other, well, I guess more than 4 because the rotation matrix, there's 3 varieties. Plus, we should also have a basic identity matrix. That'll be the starting model matrix for all our geometric objects. So we're going to get back to coding. It's been a while, but here is our graphics framework as it stands. It's been about 7 or 8 videos since we last created a test example. That's a lot of mathematical theory. So our first task is going to be to create a matrix class. Now, we're going to be using a library that we previously installed, the Python library NumPy, and that can handle matrix calculations. What we need to do is create a class that can generate the different kinds of matrices that we're going to need for 3D graphics. So, right here, I'm going to start off. I've opened up my favorite development environment, Sublime Text. And here's my Python graphics folder. The matrix class is going to be one of our core classes. So within the core folder, I'm going to right click and make a new file. And I'll go ahead and immediately save that. I'll call it matrix.py. Okay. For this one, we're going to start off right away by importing the NumPy class, the NumPy package, which we've previously installed. And because we're going to be doing some work with trigonometry, as you might recall, from the math package, we need to import sine, cosine, tangent, and pi. All right, let's create a class called matrix. And again, the point of this class is really to generate the matrices that we need. So really everything in here is going to be a static method, so we can just call it straight from the class. So let's start off. Let's go ahead and make an identity matrix. That'll be our starting point. For every static method that we're going to want to create, we can start with this decorator at static method. I'll define a function called makeIdentity. Let's see, and all of these are just going to return a NumPy array, a NumPy two-dimensional array, which we call a matrix. First row is 1, 0, 0, 0. Next row, I like to line these up, 0, 1, 0, 0. Next row, 0, 0, 1, 0. Final row, 0, 0, 0, 1. Again, whenever we initialize a matrix, it's going to be an identity matrix if it's the model matrix for something. Also, we have to be very careful. NumPy, if we create a matrix like this, NumPy will assume that all the numbers are integers, which they are, but we'd actually like them to be transmitted as floats. So I'm also going to add as type float. Right, that way everything will get casted to the right data type that we need for uploading to the GPU later. All right, let's go ahead and let's make some more matrices. Static method. Let's go ahead and do the make translation next. This one will take some parameters, x, y, and z, and that'll form the third column in our matrix. So here we need to return a NumPy array using, nope, not those, but those. 1, 0, 0, x. Next row, 0, 1, 0, y. Next row, 0, 0, 1, z. Last row, 0, 0, 0, 1. As type, float. All right, next let's make some of those rotation matrices. Let's do make rotation x. For this, we really only need an angle, and we're going to assume that's passed in terms of radians, which is what most mathematical functions in computer science need. To make the code more readable, let's store the cosine in the variable c. Let's store the sine in the variable s. And now let's return our NumPy array. 1, 0, 0, 0. Next was 0c negative s 0. Next row, 0s c 0. Last row, 0, 0, 0, 1. I do like to line these up. It makes it easier for me to check my work. As type float. All right, next matrix. Static method. Let's make rotation around the y-axis next by some angle. Once again, c is cosine of that angle. S is sine of that angle. We'll return a NumPy array. See, first row is C0, S0. Next row, 0, 1, 0, 0. Next row, negative S, 0, oh, negative S, 0, C, 0. And last row is 0, 0, 0, 1. Oh, I forgot a opening and closing bracket there. And I always like to line these up. I don't want to forget as type float. All right, we have one more axis that we can rotate around. Let's add that in. Static method, make rotation z. Again, no surprise. Let's store the cosine and sine of the angle. And now let's return our NumPy array. Right, this is going to be, I like this one. This is the generalization of two-dimensional rotation around a point into three-dimensional space. So this is going to be C negative S 0, 0. Next row is S C 0, 0. Next row is 0, 0, 0, 1. Last row is third row is 0, 0, 1, 0. Last row is 0, 0, 0, 1. Let's line those up. Nice. Still type float. All right, we have next the scale. Now, scaling is a little bit weird. If you do something like a local scale combined with a rotation, it actually starts to make things look a little bit strange. So really, the main kind of scaling we're going to need is a uniform scale, meaning every coordinate gets scaled by the same amount. So we're actually going to create a static method which takes only in one parameter, and that'll scale all the coordinates by that amount. Okay, in this case, we just need to return a NumPy array, S0, 0, 0. Next row, 0S 0, 0. Next row, 0, 0, S 0. Last row, 0, 0, 0, 1. As type float. All right. This last one, the big complicated matrix. This is going to be perspective. So static method. Now we're going to define make perspective. All right. So let's see. I'm going to do angle of view first. Here, what I'd like to do is provide some default parameters. And so I'm going to say 60 degrees is an angle of view. For the aspect ratio, our window is spin square, so I'm going to use the default aspect ratio of 1. Near distance, I'd like to see things up close, so maybe I'll do 0.1. And far distance, maybe I'll do 100 for now. And of course, anybody using this function can supply different values for these parameters if they want to customize their camera a bit more. All right, so you might notice here I'm writing angle of view in terms of degrees. So the first thing I need to do is convert that to radians. So the formula to convert coordinates into radians, let's see, I'll call that A. It's going to be the angle of view times pi divided by 180. That's why we needed to import pi from the math package. Next, that formula, just for convenience, I'm going to write d. This was the distance to the adjusted viewing plane. This is going to be 1 divided by tangent of a over 2. Again, just to make the matrix easier to read, let me call r the aspect ratio. We used the number b. It's going to be far plus near divided by near minus far. And then the number c is 2 times far times near divided by, again, near minus far. Right, those were the values we used when we were deriving the matrix. All right, now we're ready to set that up. So we're going to return numpy.array. Right, this is d over r, 0, 0, 0. Is our x scale. The y scale was 0d, 0, 0. The z adjustment was 0, 0, bc. And then finally, that weird perspective divide trick was 0, 0, negative 1, 0. As type float. Now let me go ahead and line these up. And how's the matrix that we derived? Cool. Okay, we've got a matrix class. We're going to use this to produce matrices. And we're pretty much ready to start creating a new graphics program. One thing we'll have to do before we actually dive into the application, this is a new type of data that we want to upload to the GPU. We've worked with floats and vec2s and vec3s and vec4s. This is the first time we're working with a 4x4 matrix. So we're going to need to make a little change to our uniform class. So I've saved matrix.py, that looks good. Go ahead and open up the uniform class. So previously, we have not worked with matrix 4s. So we're going to add this as a new viable data type. So I'm going to put that in the comments. And then, let's see, so down here where we have our else if statements, I'm going to insert a new else if statement right down here. If self.datatype equals mat4. It's a 4x4 matrix. Turns out the OpenGL function we need is GL uniform matrix 4FV. So it consists of 4 float vectors. Now what do we need to put in here? Of course we need the reference to the variable that we're going to use. This takes a few more parameters as well. So you could theoretically send more than one matrix. I'm not sure why we would want to. I don't think we will. So this next parameter is just going to be 1. The next parameter is interesting. When OpenGL works with matrices, it expects the data to be arranged column by column. And that kind of makes sense because when we derived the matrices, we usually applied the transformation to those basis vectors, and that gave us the columns of the matrix. But the way we entered the matrix data with NumPy, right, this is formatted as being entered row by row. So what we need is we need to switch the rows into columns. That's an operation called transposing a matrix. And so to signal that we need to transpose it, we pass the constant GL true. And finally, the last piece of information we need is self.data. We want to actually send that matrix there. All right, very cool. I think we're pretty much ready to go ahead and start a new application. So what video is this? I think it's video 22. So let's see if we remember how to do this. I want to put a new test file in our root directory, so not the core directory, but the root directory. So let me go ahead and make a new, let me save uniform.py first. Cool. Oh, I want to save that. All right. I'll close those down. Okay. In the Python graphics root folder, I'm going to create a new file. I'll go ahead and I'll immediately name that, maybe test22.py. All right, so first we've got a bunch of import statements. So let's go ahead from core.base, import base. I have to be careful it doesn't autocorrect to lowercase. From core.openglutils, import capital O OpenGLUtils. From core.attribute, let's import attribute. I hit another space before I hit enter. It stops the autocorrect from taking place. From core.uniform, import uniform. And now our brand new class from core.matrix, import matrix. Right, that'll allow us to generate all the different matrices we're going to need. We also need everything from PyOpenGL. So from opengl.gl, import all the things. And from math, import pi, because hey, pi is useful. Okay, in this application, we're just going to go ahead and move a triangle around the screen. If you've ever played the really old arcade game Asteroids, it might evoke some memories of that. Okay, so let's go ahead and comment this. We're going to move a triangle around the screen. And I call all my classes test. They always extend to base class. Def initialize. That's one of the methods we need to implement. And so I'll print a little message, initializing. And let's go ahead and write the shaders. All right, this is multi-line, so triple quotes. In vec3, I need to take in a position. And now, fun part, we're going to start using these matrices. And it's going to make the shader code just really nice and easy to read. So they're uniforms. Right? The same matrix is applied to all the points. We're going to do a projection matrix. And uniform mat for model matrix. Now we can go to void main, calculate GL position. What do we need to do? Well, we need to take our position, then we'll adjust it according to the model transformation, which will kind of move it around in space. And then the last thing we'll do is the projection, the perspective transformation. So projection matrix times model matrix times vec4. Here I'm using a shorthand notation. Instead of saying position.x, position.y, position.z, vec4 is overloaded, so it'll actually take position, which is a vec3, split it into 3 coordinates, and add 1.0 as the fourth. I love writing shaders. All right, so again, matrix multiplication happens from right to left. Build our vector. We now know that this is for homogeneous coordinates purposes. Right? It enables us to do translation and perspective. Multiply it by the model matrix, then multiply it by the projection matrix. That gets stored in GL position. And that's really all we need to do for the vertex shader. All right, so we can close that triple quote. And next we'll write the fragment shader code. Doesn't have to be very fancy. Right, the point is to use matrices. Let's see, so I'm going to do an out vec4, store the color of each fragment, void main. So frag color is equal to a vec4, be whatever color you want. I like yellow because of the contrast on black. There we go. There's our fragment shader. All right, so I need to close that with a triple quote. And let's see, I'm going to go ahead and compile that program on the GPU and store that. We'll call that program reference. Those compilation functions are in the OpenGL utils initialize program with VS Code and FS Code. All right, so that will compile it. We'll get a reference to the program, which we can activate later. All right, so next we'll do some render settings here. We can do things like define the clear color. And so I'll just use black, but you could change this to a different color if you want. And there's actually something else we need to do as well. We need to enable depth testing. By default, objects are just rendered in whatever order that you call the draw function on them. If you actually want OpenGL to compare depth coordinates, to compare z coordinates, we actually have to activate that with the OpenGL function GL-enable. Right, so GL depth test means yes, please use depth testing. We're going to go ahead and set up vertex array objects, or VAOs. That stores all our vertex binding information. In this case, I don't need to assign it to a class variable because we really only have the one. So we have to declare it and activate it. But again, because we're not switching between multiple objects, I really don't need to store this for later. So we generate it with GL gen vertex arrays, and then we activate it with GL bind vertex array, VAO ref. All right, now we need the vertex attributes. In this case, really, it's just position. And again, the ultimate goal here is to make sure that the matrix multiplication works. So first, I'll set up an array of position data. This will be 3 vertices, so it'll be a small isosceles triangle. 0.1, negative 0.2, 0.0, and negative 0.1, negative 0.2, 0.0. Maybe I'll arrange these nicely. All right, so 3 vertices for an isosceles triangle. Sounds good. All right, next we need to store how many vertices there are. Again, we know that there's 3, but I like to establish the habit self.vertex count. That's going to be equal to the length of position data. All right, now I can set up my attribute using the attribute class. And remember, the attribute constructor takes 2 things. First, a string saying what the type of data is, and then the actual data. And so that loads it up. Next, we want to associate this attribute. We want to associate the vertex buffer to one of the variables in the shader. Right, so we do that with the position attribute function associate variable, self.programRef, and we're associating that to the variable called position. Excellent. Next, we're going to need some uniforms. You might recall from a minute ago, we declared 2 uniforms, a projection matrix and a model matrix. So we need to set those up next. And this is where our new matrix class shines. So we'll say, let's say mmatrix equals, from the matrix class, we're running the static method make translation 0, 0, negative 1. And the idea is when we start, the virtual camera is at the origin 0, 0, 0, and I need to push this away from the camera a little bit. Right, so I'm pushing it kind of into the screen so it shows up on camera. That's why I have this initial negative 1 in the z component. All right, so that matrix data I'm going to put inside a uniform object. So self.modelMatrix is equal to a uniform. Again, this is our new type that we just added to the uniform class, mat4. I'm putting the model matrix in there. And then, again, just like we find out the association for an attribute, we need to do the same thing for a uniform. It's slightly different, but similar. It's the same, but different. Locate variable. And this is going to be self.programRef. And then, again, the name of the variable as a string. We called it model matrix. Now we want to do something very similar for the projection matrix. right, so I'll start off with P matrix equal to matrix dot make projection. Oh, no, make perspective, I think we called it. In theory, perspective. In theory, there's two different kinds of projections we can do. Right? There's the perspective projection, which makes objects smaller away, smaller in appearance the farther away they are from the camera. There's another type of projection matrix called an orthogonal projection, which we might cover in a future video, but for now I really want to focus on perspective. And we'll use all the default values for the parameters that we set up in that function. All right, now we'll actually create our uniform object with this data. We'll call this self.projection matrix equal to a uniform. Again, the type of data is mat4. The initial data is stored in the variable p matrix. And we need to locate the variable and self.programRef. This is going to be attached to something called projection matrix. All right, those are our uniforms. Now, hey, let's go over to the update function. Right? We've got everything set up that we want. So I need to indent by one layer. And let's define the update method. And again, it's been a while since we've done an application. The update method is the other function that we need to implement that's defined by the base class. So really what we need to do here is we're going to move a triangle around the screen. So there's going to be a lot of input detection. Right? So let's say, for instance, if self.input.isKeyPressed. And really I want to test both kinds of motion, both global and local. Right? So I'm going to use different key combinations for these. So first I'll do global transformations. We talked about that in a recent video. So in this case, let's say W will move something up. So let's say M equals, from the matrix class, we will make a translation matrix, right? And we'll translate by some movement amount. Rather than coding it in here, let's create something called move amount. It's going to be something kind of smallish since this happens 60 times per second. So maybe I'll do that for move amount. So move amount and 0. Okay, so we make our translation matrix. Since this is a global transformation, we want to take the model matrix and multiply on the left side. So self.model matrix. Remember, this is a uniform object that stores data. So we're not multiplying this, we're multiplying the data stored in this. So we want to do m times the original model matrix data. One of the interesting things about NumPy is that it overloads some operators, but it does not use the asterisk to indicate matrix multiplication. It actually uses the @ sign. So at self.modelMatrix.data. Again, this symbol is used for matrix multiplication. Cool. Now we need a whole bunch more of these statements. So these are going to be global translations. And so really I need a few more of these. I need 3 more copies. And this is going to correspond to movement in each direction. So W is up. We'll make S down. It's down on the y-axis. We'll make maybe A be left. And so that's negative x-axis. So negative move amount corresponds to A. And then D is going to be movement to the right, or technically these are global, so I should really not say things like left and right. I should say positive along the x-axis. All right, so those are our 4 of our global translations. Before I get too much further into this, maybe I'll go ahead and add in some of the rendering code before I add in all the other transformations, just to make sure everything's okay. So that's a global transformations. Now let's say to render. What do we have to do? GL clear. So in the past we've just cleared the color buffer. We also need to clear the depth buffer, right, in case things are moving around, which they most certainly will be. So I also want to clear the other buffer bit. And the way these are combined, these are really bits, so to combine 2 kind of bit numbers, we use the bitwise OR operation. Let's see, we'll do GL use program next. That's in program ref. Next, we need to upload the projection matrix and the model matrix. So self.projection matrix, that uniform. Go ahead and upload your data to the GPU. It's not really changing a lot though. It's not really changing at all. And then we upload the data for the model matrix, which will change a lot. Then we can do GL draw arrays. And that, in this case, we want to render it using the triangles draw mode. Tell how many vertices to render. All right, moment of truth. Let's see if this is okay. If I go ahead and see it's saved, let's go to Tools, Build, and see what we can see. It might have been a typo, I'm not sure, until this actually starts running. You know what? It's not that there's a typo so much as there's nothing to run. I've forgotten this a couple of times before. I need to instantiate and run this class. So what do I need to do? I need to create an instance of the test class and then activate its run function. Ooh, let's try that again. All right, let's see, locate variable. Again, it's been a while since I've done this. Let's see, test object has no attribute locate variable. Oh, so up here, I actually need to say the name of the uniform. All right, so self.model matrix and self.projection matrix. All right, with those 2 fixes, and actually using the methods of the objects, let's try that again. Save and build. Hey, we have a triangle. Let's try moving it up, down, left, and right. Cool. So we know that global transformations so far seem to work. Very nice. All right. Next, we're going to go ahead and try adding in the rotation as well. Right, before we were able to do some translation, right, that was actually what we did in test 14 a long time ago. Rotation's a lot more complicated though. Right, so let's add in some global rotations next. So right before the render function, let's add in a section for global rotations. Now, there's a particular kind of system I like to use for the different keys, since we're going to be using a lot of keys on the keyboard. Usually on the keyboards that we use, these are called QWERTY keyboards. Apologies to anyone who's using an AZERTY keyboard. But we use the keys WASD because they're laid out in the same style as the arrow keys. What we'd like to do is create some mnemonics so we kind of remember what each key does. I really like to use Q and E for rotating left and right. The reason being, Q is right above A, So rotate left is right above move left, or strafe left. And E, rotate right, is right above D, which is move to the right, or move along the positive x-axis is what I should say, because again, these are global transformations. All right, so for global rotation, remember this is going to be around the origin. Same kind of format. How much of this can I copy? A fair amount. All right, so for rotating to the left, or that is rotating around the origin counterclockwise, what I'd really like to do is, let's say, matrix dot make rotation z. And so rotating around the origin, that's like rotating around the z-axis. And I need to specify some amount here. Just like I did for move amount, maybe I'll create some kind of variable called turn amount. Again, this is in radians, so something small. I'll try this. If it feels too fast, I can always change it later. Like move amount seemed fast, so I'll lower that down a bit. So that'll be turn amount. I'll set that to 0.01. I'll use turn amount here. Right, when we set up the rotation matrices, we assumed that was in radians. All right, so that'll turn us, or rotate us around in one direction. We'll have the E key, rotate around the origin in the opposite direction. And these are global, so I'm multiplying by the transformation on the left. And that becomes my new model matrix. So again, save, and let's build that again. All right, so I can go up, down, left, right. And now if I push Q, the triangle is actually rotating around the origin. And I'll position my highlighted mouse right there, so you can see it's kind of going around. If I press E, you'll see that I'm going in the opposite direction. In fact, I was feeling a little bit fancy, and I set up a screencasting keyboard, which I forgot to turn on. Again, you can see that here I'm moving up and down, left and right. And again, Q rotates around the origin counterclockwise, and E moves around clockwise. Again, I like this method because E is above D, and Q is above A. Excellent. All right, next we're going to go ahead and try out the local movements. All right, so it's going to seem very similar to, in fact, all of this code. So I'm actually going to go ahead and copy all of global translations and all of global rotations. I'm going to copy paste that whole block. Then I'm going to change it to local rotations. I need a new set of keys for local translations. Instead of using WASD, I'm going to use IJKL. Right, they're alphabetical and they're in the same alignment. So I for moving local up, K for moving local down, A for moving local left, and L for moving local right. Now to make these local, remember I have to multiply in the opposite order. All right, so I'm going to switch each one of these to multiply on that side. All right, so that should be local translations. I'm going to change global rotations to, I can spell local rotations. And again, same kind of layout as before. I'm going to use the keys above local left movement and local right movement for local left turn and local right turn. So U is above J and O is above L. Again, I just want to make these multiply on the other side. times m times m. All right, so we should have local rotations good to go. Let me save and give this a build. All right, and here's my screen. I'll leave my mouse right here. So again, I still have global movement, but now I'm going to do, let's move it kind of up and over here. Now let me try some of the local rotation first. So pushing O, I spin to the right. Pushing U, I spin to the left. So I'm spinning around the center of that triangle. Next, I'm going to push I. I is local up, which was towards the direction of the top thin angle. Right? And K is local down. J is local left, and L is local right. So again, if you've ever played the very old arcade game Asteroids, I'm very much hit with a wave of nostalgia, and I'm thinking about that. Very cool. Right, the last thing I'd like to do is test out the perspective matrices. You notice I haven't added anything for translation around the z-axis yet. Right, so I definitely want to see if I move it forwards and backwards, will it get larger and smaller? Hopefully the answer is yes. All right, so I'll add this in global translations. So I need to copy 2 of these. Let's see, we run out of keys fast. Let's see, I'd like to use, for moving along the z-axis, hey, let's use z. In this case, I want to move the positive z-axis. So that's move amount. And then, I guess next to z is x. So I'll make that move along negative z. So negative move amount. And again, it's a global transformation, so that's why I multiply by the matrices on this side. Fantastic. Let's go ahead and give that a build. All right. So again, I can move the triangle all around. But now let's try pressing Z. Sure enough, it's coming right at us. Whoa, and eventually it disappears. Right, that means it's moved past the near distance, past that limit, so it no longer shows up on the camera. It's moved out of clip space. Pushing X will bring it back in, and it's being moved further away from us. And I can still do all the other transformations. I can still move it around. Yep, Z and X make it closer and further away from the camera. Right here, I kind of positioned it up and to the left. And then as I kind of pull it closer, it looks like it's moving off to the right. But that's really the entire z-plane is shifting towards us. Excellent. So, hey, all that work with matrices has paid off. And this has been quite a long video. It's been a while since we've done some coding, so we did a whole bunch of coding. And I hope you feel as though all that time spent learning mathematics was useful. This is everything we really need to do to move things around and customize our scene. So you might wonder, what's next? Well, there's been a lot of steps in this video which seem to take a lot of time. Whether it's this movement controls, or we always need to set up an attribute and a uniform and these different matrices. We're going to start to automate a lot of these steps, right? Setting up the render settings and the uniforms and the render process, calling GL draw arrays. We want to start to build the framework around accomplishing these tasks for us. So we're going to start kind of a whole new chapter in the next video. We're going to talk about the overarching framework that we're going to use to do 3D graphics, kind of incorporating all these classes. We'll have new classes for different 2D and 3D geometric shapes. And it'll simplify the whole scene building process. So I hope you enjoyed moving that triangle around the screen, and thanks for watching.